Hello everyone. Welcome back to ComSci Connection. This is part 3 of the graphs video. This is going to be a walkthrough of breadth first search. We did depth first in part 2, and we did the introduction to graphs and to specifically my graph code in part 1. So if you have not seen those, or if you're not familiar with graphs in general, I would recommend checking out one or both of those videos. And then join us back at this point. But if you're specifically here to learn about breadth first search, then you are in the right place. Let's get right to it. As before, I have, not that one, I have this representation of a graph that we will be using for the purpose of this video. It's the same one that I used in part B and the same one I used in part A. So it hasn't changed at all, but now the actual path that we're going to be taking is going to be different, because in the depth first search video we traversed this depth first. So we followed down a single limb or path or tree, or however you want to look at it, a single path down the graph until we reached an end, and then we went back up to another point where we can fork and continued following individual paths down, depth first. In this video, we're going to illustrate breadth first search, which is essentially, whereas depth is deep, breadth is referring to width. We're going to go outwards instead of going down. So we're going to see a different type of traversal displayed in this video, and because of that, a different methodology, a different algorithm altogether. So let's do the same thing we did in the last video and look at the actual code first. So you'll notice in my last video, in depth first was done recursively. So I had an initial method which called it, and then I had a recursive method that the initial method called. And in this video, there is not recursion with breadth first search. It just doesn't work. So you have to do it a little bit differently. And in this video and in this algorithm, we are going to use a queue. So essentially what I've done here is I've got a starting vertex that I'm taking in, accepting in as the starting point. What I'm going to do is, just like depth first search, I'm going to store a set of visited nodes so I can make sure that I don't double up on the nodes that I'm visiting, or the vertices that I'm visiting, excuse me. And then I also have defined a queue. Don't be thrown off by the use of deck here. It's just that, fun fact, deck is what you're supposed to use rather than using the queue interface. You should use the deck interface whenever you're using a queue. There's lots of reasons for that. I won't get into it, but it's just better to take my word for it. And you'll notice I've instantiated the deck or my queue as a linked list. Those are just little details. We're not going to focus on that. The first thing I have done is added the start vertex to my queue, so I have one item in there, and then I've also added it to my list of visited vertices. Now that's weird, right? Because in the previous video I made such a big deal about the fact that I added my current node to my list of visited nodes right after I visited it, but here I'm adding it to my visited nodes before I've actually visited it. Yes, I added it to the queue, but I haven't actually visited it yet. I haven't actually printed it to the console. I haven't done anything useful with it. So why would I do that? Well, simply put, in the breadth first search, it's very possible that you may run into other methods which are going to connect to the same vertices that you already have in the queue, but you have not yet visited them yet. In breadth first search, or excuse me, in depth first search, you're guaranteed that if you've reached a node at some point that you haven't already visited it yet, you haven't already done something useful with it, you're guaranteed that that's the first time that you've come across it, because you always visit nodes in that fashion, where the first time you come across it, you visit it right away, and then you recursively traverse down any of its edges that it has connected to it. And so if you run across that node again, you're guaranteed that if it's in the visited list, you've already seen it and you've already visited it. But here, you might end up running into a relationship like here, where H might add F to the queue and then D would get visited before H has actually visited F, or before you've actually visited F. So you want to make sure you avoid that doubling up, and that is why I stressed that so much in the depth first search video, and again why I'm beating this dead horse in this video, is there's a subtle difference in when you actually consider a node or vertex checked off. And so in this case, I have done that immediately after I added it to the queue. So, enough of that nonsense. Let's jump right into the actual algorithm. So, as you'll note, I did add one item to the queue before I did anything else, and now I'm going to start this while loop that says while the queue is not empty. Well, of course we know the queue is not empty. We have at least one item in it. So what we're going to do is pull off or dequeue the top item in our queue, the one that's next up in line. We're going to store it as a vertex called current, and then we are going to visit the vertex by simply printing it. And now in the depth first, this is where I added it to my list of visited vertices, but in this video obviously I don't have to do that. So now I'm going to store a list of edges, just by simply asking current to return its list of edges to me. Same as last time. We're going to go do a for each loop to go through each edge in edges to store the direction that we're going, or the vertex that we're heading towards, as a vertex called next. Store the reference to it as a vertex called next. And then we're going to check to make sure I haven't already visited that node. Same as last time. But now this is a bit different. Instead of a recursive call going in this section of code, I'm actually just adding it to the queue and then also adding it to my list of visited vertices. So I guaranteed I've already essentially checked it off, so I won't see it again. And that will cause the loop to end and start back up at the top here at this portion of the loop. So we're going to go back up to the top and pull off the next item. So essentially, how is this going to look? Well, obviously first, if I start at A, I only have one edge that I can possibly traverse, so A will take us directly to B. But now, B is actually going to go through a loop process and add each one of its edges that point to a specific vertex. It's going to add that vertex to the queue. So we essentially get this behavior. The pink here is going to represent a node which has been added to the queue, and you can also safely assume that it has been marked visited for the purposes of this video and for breadth first search in general. So now that B has added C, D, and E to the queue, we're essentially done with B, right? I mean, we've visited B and we're done with it. So again, I mentioned this in part B, but for the purposes of the graph traversals, I always did them in such a way that you can always guarantee a left to right traversal. So the return values or the list of edges will contain in this order C, D, and E. My advancement there didn't really show that, so I'm just going to explain that C will be before D, and then D will precede E. So the next item that will pop off the queue is C, and C will go ahead and be considered, or it's already considered visited, but we've now actually done something useful with it, and we're going to essentially pull off all of its edges. So we have just H, which has been added to the queue, but unlike depth first search, you'll notice that now when I ask for the next item on the queue, we are not going to go further down the trail of B, C, H. We're actually going to find that D is the next item. It's been waiting longer than H has, and also longer than E, so it's next. D will add its items to the queue, F, and then G, and then the next item in the queue is E, so we'll visit E. E will add its item into the queue, which will be K, and then now we know that the next item to visit is going to be H, which would be the most, or the one that's oldest in the queue. It's been waiting for the longest time. And now you should really start to see where the term breadth first search comes from. Where in depth first search I went down a specific path. In this search I'm going to expand my path all the way out first, and then kind of follow each trail down intermittently, one at a time. So C will lead to H. H is now being considered visited. H will add all of its edges to the queue, but F has already been added to the queue, right? We haven't actually, and this is important to notice, we haven't actually done anything useful with F yet. It's still in the queue and waiting, hence the pink. But the relationship or the edge from H to F is colored purple to signify that it has not been added to the queue again. We already count it as visited, even though we haven't actually traversed into F yet. We're going to ignore it because we've already at least added it to the queue, and quite possibly have actually done something useful with it. In this example, we haven't done anything useful with it yet, but we have added it to the queue and it's still waiting. And in fact, it's the next item. So what we're going to do is completely ignore that edge and just quit. So now we'll pull off the next item off the queue, which is F. So now we visit F, and F will add its edges, or its vertices that its edges connect to the queue. So we add I. The top item on the queue now is going to be G, so we're going to visit that, and we're going to go ahead and add J into the queue. And then the next item on the queue that's been there the longest is K, so we'll go ahead and visit that. And then again, we're going to look and see, hey, at K, what edges do you have? Okay, great, you have one. All right, what does that connect to? It connects to J. I've already added J to my list of visited edges, so it is at the very least in the queue. So let's just go ahead and throw it out. So we'll mark it as purple. Now, of course, we know that I is still waiting in the queue, so we're still going to visit that. And then our last node to be visited is J, and we're going to go ahead and visit that. And we're done. So let's go ahead and take a look at this in action. So let's reduce the size of the console. I had that blown up from the purposes of the last video. Let's step into our breadth first. And alright, so we're going to start here with our visited, which is just an empty set. We're going to start our queue, add the first item into the queue so we can see that the queue has some first item, which is this, and it has data A. Let's see if I can make that just a bit bigger so we can see more stuff. Okay, and then we're going to add it to our list of visited edges or visited vertices, and then we're going to start our loop. So while the queue is not empty, well, of course we know the queue is not empty. It has one item in it, so we're going to pull that item off. Now current will refer to A. A is going to get its list of edges. For each edge in edges, we're going to pull off that item. We're going to look and see that the next item is B, so we are at this point. We're basically going to add it to the queue and then add it to our list of visited. Next edge, well, that's it. That was the only edge. So now we're back to, is the queue empty? Well, no, it's size 1. We just added B into it. So we're going to go ahead and pull current off. You'll notice current is B. Then we're going to visit B by printing it to the console in this case. Get the list of edges for each edge. Let's get the next one. Let's check to make sure we haven't already contained it. Add it to the queue. Add it to our list of visited. Let's do the same thing for the next one. Get the next edge. Check to see if we haven't already contained it. Or if we visited doesn't contain it. Add it to the queue. Add it to our list of visited. Same thing with the last one. So now that loop will finish and we're back to the top. Now a couple things. So we are at this point, we've added C, D, and E. If I look at the actual queue, I will notice its size is 3. It has 3 vertex items in here in that mumbo jumbo. First item is C. Next item after that is D. And then the next item after that is E. So that's exactly what we expect. C, D, and E in that order. So we'll go ahead and pull off the next item off the queue. Current is going to be C. Print it to the console, get the list of edges, go through each edge, add it to the queue, and then add it to our list of visited. And that's it for C, because it only has one edge. It has H. We are here. Now we will step forward once again, pull off the current item. I'm going to collapse my queue. My current item is D. Let's visit it. Let's go